Good morning, dear students. Yesterday we discussed about all the static characteristics and now I have to discuss about dynamic characteristics. So yesterday in the classes I gave some brief introduction about the dynamic characteristics. So when we need to consider the dynamic characteristics of a measurement system relate to its performance, and the measurement is function of time. So what is measurement? Measurement is nothing but the quantity which is to be measured. So if the quantity which is to be measured is the function of time, at that time we need to identify the dynamic characteristics of a instrument. So what are the inputs? Those are the function of time. Let us see. So you know very well about the step input. So it will have the constant value up to infinite time from 0. So this can be called as step input. So the next one is ramp input. So it can linearly increases from the origin to infinite value. So with a certain slope. So let us assume it was m. Here in this case it was k. So similar way the sinusoidal input. So sinusoidal input also a function of time. So f of t here is Vm sin omega t. So similar way. So these are the three main inputs we have while considering the dynamic characteristics of a measuring system. So these are three elements. By using these three inputs, we can able to check the dynamic characteristics of a measuring system. So this dynamic characteristic of instrument involves in. So likewise, the static characteristics, it has 19 parameters. So we have to check those 19 parameters so that we have to go for selection of transducer. So while checking the dynamic characteristics are involved in the following. The first one is dynamic error. So similar like the static error, here it was dynamic error. The second one is fidelity. So fidelity means how the instrument is measuring in a good way by instant to instant. Why? Because here the measurement is function of time. So that means if the time changes, the input will be changes. So fidelity means the instrument must need to identify the input signal if the time changes as well. So it needs to identify instant by instant even if the time changing. So this can be called as fidelity. Let us see later. So the next one is bandwidth. So we know that the bandwidth is nothing but the range of frequencies. In the range of frequencies, if the instrument is providing a satisfactory results, so that will be the bandwidth of that instrument. So that is also we can see later in detail. So speed of response. So if the measurement is function of time, how the instrument is responding well. So that means how much speed it was activating for the time changing input. So let us see in detail about this also. So the first one in the dynamic characteristics is dynamic error. So what might be the definition of dynamic error? It is similar like static error. So there will be no change of input with respect to time, but here there will be change of input with respect to time. So measurement is the change. Measurement can be changed with respect to time here. So what is the definition is the algebraic difference between the indicated or recorded value and the true value of the measuring system, and the measurement is function of time. So simply we can call this as the algebraic difference between the output and input of the system if the input is function of time. So here input means the quantity which is to be given. So it is nothing but measuring. And the output is the indicated value here, indicated value of the instrument. So it's the function of time as both the measurement and the output signal of the measuring system is function of time. So here in this case, if input is already we can told as it is function of time. So similar way the output also function of time. So dynamic error is also the function of time. So here the both cases, that means input is function of time as well as output is function of time. So hence the dynamic error also the function of the time. So it is only in the ideal case for zero order measuring system. So So in the ideal case means it will be 0. It is only 0 here, the 0 was not printed. So it is only in the ideal case of 0. So it was interchanged. So please consider that mistake. It is only 0 in the case of 0 order measuring system. So for the 0 order system only, it will be ideal. That means it will be 0. The dynamic error will be 0. But practically it is not possible. So most of the systems will be either first order or second order. So for the higher order system, the dynamic error has two component system. So if you consider first or higher orders, the dynamic error will have two components. So the first one is transient error and the second one is steady state error. So what is transient error and what is steady state error? So transient error. So that means the instrument is stable up to if you gave some input to that. So up to that it was stable. If suddenly if you gave some input, it has to respond for that. So that can be called as speed of response. So while responding, so the sudden changes occurs now. So at that time it can show some error. That error can be called as transient error. So the error that occurs at the sudden changes. So that means after time it will reach us to our output. That means steady state value. So even after steady state value, it may show some error that can be called as steady state error. So that means the error that occurs suddenly. So when you are giving the input, at that time it can show some error that can be called as transient error. Sometimes the needle will go upward direction and thereafter it will come back so that it will stable at some time, at some place. So after that, even after getting the stable, it may have, it might not show the true value. So it might have some difference, and that difference can be called as steady state error. So after giving some input, it was going to the higher value, which can be called as transient error. After reaching the steady state value, it might not show the true value. It might have some difference, but error can be called as steady state error. So steady state error. So the steady state error we need to consider in three ways. So what is the ways? So there are three types of inputs: step input, ramp input, and sinusoidal inputs we can use in dynamic characteristics. Otherwise we can use those are for instruments. So generally these are the three time-based inputs we can give to the instruments. So if you consider, if the instrument is subjected to the step input, then the ratio between the output to the input can be called as static sensitivity. If the measuring system is subjected to the step input under steady state, the ratio between the amplitude of output signal and the measuring signal, so measuring is in the sense input signal, is called as static sensitivity. So what will happen if it was subjected to ramp input? So if the measuring system is subject to the ramp input, the ratio is constant. So in this case, the ratio is constant. So the steady state error is constant. So it will be useful for calibration. If it is always constant, we can able to calibrate it. So the next one is, if the measuring system is subject to sinusoidal input, the ratio between the peak amplitude of the output signal and the input signal is called as dynamic sensitivity. So here the step input. So it will changes only once. At 0, it will have suddenly rises to some amplitude. Thereafter, it will be constant. So that can be called as static sensitivity. But here in the case of sinusoidal input, it will always changes with respect to time. So it will go maximum value, thereafter it will reach us to 0, and it will go minimum negative value, and thereafter it will reach us to 0. So here it will be in dynamic case. So here the ratio between the output to the input can be called as dynamic sensitivity. So these three factors we can consider for the steady state error. So the next one is fidelity. Fidelity, I already told you, it is the observation of the instrument against the input instant by instant. So definition. So So fidelity of a measuring system refers to its ability to follow instant by instant variations of the measuring with time. Measured with time. So if the measurand is always varying with respect to time, so the instrument must follow those with respect to time. So if it was following instant by instant, it can able to show the accurate values. So let us take the temperature. It will always changes. It will always changes. So the temperature meter must need to identify the temperature by instant to instant. So similarly, fitness bands. So fitness bands can identify the heart rate. So fitness bands can identify the heart rate. So it need to identify our heart rate instant by instant. So all these are the examples for the fidelity. So only the zero order system gives excellent fidelity. I already told you. So the dynamic error also zero for the zero order systems. So most cases the dynamic systems are second order or first order systems or otherwise higher order systems. So practically this won't happen. So but not for the case of higher order systems. So the fidelity will be excellent for the zero order system but not for the higher order systems. So the requirement of the fidelity differs with the application to application. So it will be differs. So few instruments may need to identify selection for the selected range of frequencies. So that means lower frequencies. For those systems, fidelity might not be good, not a problem. Why? Because at that fidelity range, it can able to identify the lower rate of frequency input signals. So no need of a good fidelity for that instruments. So let us take a CRO. The CRO need to identify frequency or amplitude step, that means time to time. So it must need a good fidelity. So such type of instruments must have good fidelity. So this point is telling about that the RMS reading MI type indicators are required to have good fidelity for a small range of frequencies. That means, so RMS indicators like us moving iron instruments, just we can give the voltage or current to that meter. So what is the frequency of our power? It's just 50 hertz. So that means these type of instruments can give a satisfactory result within the range of 50 hertz. So that no need of good fidelity for this type of instruments. So the next one is waveform readers or the CROs are required to have an excellent fidelity for a wide range of frequencies. Why? Because these waveform readers, that means waveform analyzers, otherwise CROs, need to identify the waveform instant by instant. So that these need to have a good fidelity, excellent, not good fidelity, excellent fidelity, these to have. So these are the fidelity. So the next one is bandwidth. So you know that the meaning of bandwidth is, it is the range of frequencies at which the system performance is satisfactory. So here also the same definition. It is the range of frequencies for which the dynamic sensitivity is satisfactory. Here we are talking about dynamic characteristics, so that it was dynamic sensitivity. So it is the range of frequencies for which the dynamic sensitivity is satisfactory. So this is about the bandwidth. So we can consider two frequencies, lower cutoff frequencies and higher cutoff frequencies. So it was the leading case. So we already did lead and lag compensators in the control systems. Here it was the leading case. So F1 is the lower cutoff frequency and the F2 is the higher cutoff frequency. So in between the F1 and F2, the system performance is satisfactory. So then the bandwidth can be defined as F2 minus F1. So in this range of frequencies, the system performance is good. So it was in the lead case. So if you consider the lag case, so this is the situation here. So in between the F1 and F2, so lower again, higher cutoff frequencies, the system performance is satisfactory. So this is the bandwidth for the lag cases. So here also the bandwidth is F2 minus F1. So in between the F1 and F2 range, the system performance is satisfactory. So the next one is speed of response. So the speed of response, it refers to its ability to respond to sudden changes of amplitude of input signal. So if there are sudden changes of input, if the instrument is responding very well, so that the instrument have a very good speed of response. So there are 4 terms involved to identify the speed of response of a measuring system. So what are the 4 terms? Time constant, measurement lag, settling time, and dynamic range. So these are the 4 factors we need to consider to identify the speed of the response of an instrument. So these are the time constant, measurement lag, settling time, and dynamic range. So similar like our under-damped systems response. So you can see that later. So the first one is time constant. It is associated with the behavior of the first order system. It is the time taken by the system to reach its 63.2% of its final output signal. So that means, if you consider the under-damped system response, it will be the oscillations and thereafter it will reach as the final value. You know that in control systems. You can see here also. So if it was taking to its final value, so that means in that 63 to 63.2 percentage, if it was reached at the first time, the time required to reach that value can be called as time constant. So it is the time taken by the system to reach its final value up to 63.2% of its final value can be called as time constant. So the next one is measurement lag. It signifies the time delay in occurrence of output signal due to input signal. It occurs due to dead time elements. So dead time we already know that. So dead time is the time taken by the system to respond. Sometimes even if you give the input, the system cannot be response. Right? Because of hysteresis losses, we already discussed about those things. So it cannot be response. So the lag there it was dead zone, here it was measurement lag. So in the static characteristics we consider that as a dead zone. Here it was measurement lag. So that means it won't respond up to certain time. That lag can be called as measurement lag. So the time required to respond can be called as dead time. So it will be happened because of dead time elements, otherwise the hysteresis losses and frictional losses. And this is the step input we are considering here. So for the step input, it was taking some time to respond. So that time can be called as dead time. So this is in the case of RAM input. So see that the actual input is different and the dotted line is different. That is the output. So from 0 to it was taking some time for responding. So that responsive time can be called as dead time. Here in the case of impulse input. So that is the actual impulse input as an input. So the dotted line was an output. So it is also taking some time to respond. So it can be called as dead time. So next one is settling time. The time taken to reach its steady state value is called as settling time. We already know that. So after all oscillations, it will reach a steady state value. So the time required to reach that steady state value can be called as settling time. So we already know that. So this is the general example. So the middle one is our desired value can be called as reference value, which is need to be responded. So the above dotted line and below dotted line is 0 to 5% tolerance, which is to be considered in control systems or instruments. So let us take this is the first response we considered. So this is the way the system went to the steady state. So what is the settling time here? So this is the settling time. So the 0 to the line, the yellow line can be called as settling time. So another output you can take. So this is another response of the instrument, of another instrument. So let us, what is the settling time for this? So this is the settling time. So here in the first case there are many oscillations in the starting, but it was reached to steady state as early as possible comparing to the second one. So but the second one is, it was very good in the starting state. It was exponentially rises to the steady state value, but it was taking a long time. So if you merge these two cases means, so I can have more speed of response from a instrument. So these are the two different types of the settling times for different systems. So next one is dynamic range. So what is the dynamic range? It is the range of the signal for which the measuring system likely to respond faithfully under the dynamic conditions. So for the range of signals in which the measuring system likely respond faithfully. So truly if the instrument is responding for the dynamic conditions, it will have a good dynamic range. So those range of signals and those range can be called as dynamic range. So this is about the speed of response. So the next one is errors in measurement. So no measuring system can measure with perfect accuracy. So there is no instrument can able to identify with the perfect accuracy. So we have to calibrate that instrument as per our requirements. If you want to calibrate that instrument, we need to study about errors. So it is very important to study the errors from the different sources for calibration of the instrument. In general, there are three types of errors. So the errors are classified as follows. The first one is gross errors. So gross errors are man-made errors. So the system is well calibrated. After that, we may have some we may do some errors. Okay, we may read 27.8 as 27.3. That is human mistake. So these type of errors can be called as gross errors. And then systematic errors. The errors that was done by the system we can be called as systematic errors. And the random errors. So these errors, we don't know how these errors will occur. These might be due to the environmental disturbances, or might be the lapse of the instrument. That means over prolonged periods of time, the instrument may reduce its accuracy and precision. So the random errors might be occurs due to the environmental disturbances, otherwise the system lapse. So these are the three errors we are having in the measurement. So in the next class we can discuss about these three errors in detail. So thank you dear students for today's class.